So this is the Derived distribution lab. Your notes for that, post Derived distribution lecture notes. So you have those on file, but I also kind of re-go over stuff. So derived distributions, they are distributions of functions. And in this case, the first example, we're dealing with a function. So Z is the wind tide or the waves that wind creates on a lake. And V is the velocity of the wind. F is the fetch or the length of the reservoir in feet or the lake in feet that the wind travels over. And D is the average depth. So the wave height is a function of all these things. And we want to calculate the distribution of Z based off of the distribution of V. So V is given an exponential distribution. And then we have to go through the derivation of how to calculate the distribution of Z, which is also an exponential distribution, just with different parameters. So I give you the generic formulation of the distribution of the function based off of the distribution of the random variable. And G -1 is the inverse function. So we kind of walk through how to calculate the inverse function. So I walk you through this example for the lab. For these labs, I'd like you guys to, I mean, it's fine if you copy and paste, but I'd like you guys to actually include this stuff that I do, just so that you kind of understand the first steps and plot these things. So I'd like to see, just a mirror of what I did to get there. And then you've got actual problems to do. And so we calculate the CDF of Z, and then we're going to calculate the probability that a wave height is greater than 5 feet or 10 feet or something like that. So that's what we did here. Calculate the return period for these different wave heights. And then we go over kind of different ways of dealing with design. And so we could say, for a particular design, we can choose the annual probability of occurrence and say, okay, we want to design to the 10-year wave or something like that, the wave that has a 10% chance of occurring in a given year. Or we could say we want to design so that the risk of overtopping over 50 years is, say, 10% or something like that, and you get a different answer. So there's different ways of approaching it. I want you guys to kind of go through and think about different ways we would design a dam so that it doesn't get overtopped by a wave. And that's what these questions get at. So you'll use the PDF and CDF of Z, which we calculate above. So here's the PDF of Z, and then the CDF of Z is up here. So these describe the wave height distributions based off of the velocity of wind distributions. So these are kind of like design questions, and then we get into another topic, the mean and variance of functions of multiple random variables. So this is section 4.3.2, and you can go reference that in the textbook. I also kind of give you an introduction to it right here. It's pretty straightforward for the mean. The mean is just going to be your function evaluated at the mean of all the random variables. And so say, here's an equation that represents the discharge rate in a pipe using the Manning's equation, a circular pipe. And if we say that the Manning's roughness value is uncertain, the diameter is uncertain, the slope is uncertain, with a mean and a coefficient of variation. So all of these have some sort of distribution or uncertainty associated with them. Then the expected value of discharge or that Y distribution is going to be that function evaluated at the mean values of everything. So if I want to know the mean value of Q, I'm just going to plug in the mean value of N, D, and S. The variance is going to be a little bit different, and this gets at the uncertainty equation or propagation of error that we did in hydraulics. So for those of you in hydraulics, this should be familiar. For those of you not in hydraulics, you can read about it in the lab and as well as the textbook. In which case you have to, I spell it out for you here. you have to take the derivative of the function with respect to each of those uncertain values, and then multiply it by the variance of that particular parameter value. So I walk you through all those steps for this problem, and then I ask you to answer some questions related to that, as well as a different equation, which our hydraulic students will recognize as the Darcy-Weisbach equation. So that lab, I think I have due next Tuesday. So I've been taking a look at it. Do take a look at it so we can talk about it on Thursday in class if you have any questions. But with these labs, I try to walk you through the basic steps and then ask you a question about either a similar problem or the same problem, and you know, have you guys do these calculations in R. Okay, guys, that's all I got for today. Thanks for signing in. Holler if you have any questions. I can stay on for another 5-10 minutes if you guys want to talk about anything. And then as far as other office hours goes, Carrie and I are still figuring out our schedules. I plan to have my office hours right now, at least for today, this afternoon, and then right after class, and then we'll figure out kind of a more consistent schedule as Carrie and I nail down our schedules for the week. But if you know, if there is a question, at least now that things are a little fluid, and you don't have a question right now, but you just want to chat about something, you can always email me. We can jump on Zoom or we can exchange emails. I also encourage you to use Canvas and post questions to the discussion board there, so that your other students in this class might be able to answer it, or I can answer there as well.
Hey Joel, can I ask you a question about the lab?
Yeah.
So for question 2, I got stuck on that.
Okay.
No, so for example 1, question 2, the one that it asks about the 1%.
Okay.
Yeah. Is the freeboard, we don't get a like, how do we calculate the freeboard height? Because I don't think we get that.
Okay. Yeah. So the freeboard would simply just be the same height as the wave.
Okay. And then I tried getting like the PDF and CDF of the velocity, of wind velocity, but you said that we don't need that, right? You only need the PDF and CDF of the height.
Well, so you, okay. So for question 1, basically I say you're going to create a PDF and CDF for the wave height, which is going to be based off of that. I should have been a little more clear there. So if you go back to the original problem.
Yeah, I was able to do that first part right.
Okay.
I was just confused on how to do the second part.
So we started with the distribution for velocity with that average. Okay. So I'll go back down here. And so the second part, meaning question 2?
Yeah.
Okay.
Yeah, for question 2. I didn't know how to do question 2.
Okay. So the freeboard height, again, is just going to be the height of the wave associated with a 1% annual chance wind speed, right? So the only thing that's we're assuming it has is a random variable is the wind speed. And so what you would need to do then, now that you've got the PDF, or this, I guess the CDF, we should say, of the wave height. So you could say, what is the wave height that has a probability of 1%?
Okay.
Does that make sense?
And then we'll just, yeah.
So if you set the CDF to equal 0.99,
oh, okay.
then you solve for Z at the CDF equals 0.99.
So it'd be equal to 0.99, not 0.01.
1 minus the CDF value at this wave height would be equal to 0.01. And I can just go over to like the dot cam here. Zoom controls. Okay, so if this is our wave height. And this is our CDF. It looks something like this. And if this is 1, we're interested in 0.99. So what is that Z 0.99? Such that 99% of the other wave heights are below it. And so if you have Z, so the PDF, or sorry, the CDF is going to be FZ of Z. That's going to equal to 0.99. And so we need to solve for Z.
Okay, yeah, that makes sense. I was trying to do something completely different, but
Okay.
Yeah.
And it might just be that you have to, because we don't have tables, you know, for this, and it might just be that you have to like find that, you know, by iteratively changing the value of Z until you get close to 0.99. I should say 0.99000.